about the other point solely. And it just kind of removes this whole translational component from it. It just tells you the rotation, the translation caused by the rotation about that point. It's pretty confusing actually, but you'll get the hang of it and see why this is important. Okay. So one thing that's interesting is you'll notice delta RP minus delta RQ. If you just plug these equations in, so let's take delta RP, take that equation, plug it in there, delta RQ, plug that in there, then you get this, right? Well, if we reorganize this equation, and so now we say RP prime minus RQ prime, right, like that, minus RP minus RQ, so we just took this and literally reorganized stuff. Now you can see here the same displacement, difference vector there, okay, is not just the difference in the two displacements of the 2 points, but it's also the difference in the position difference vectors. Okay, so notice RP prime minus RQ prime. Okay, so here we go. RPQ prime is, if you took RP prime minus RQ prime, that's the position difference vector at the delta t. And then we're subtracting it from RP minus RQ, that is the position difference at time t equals 0 from RP minus RQ, which is this one. And you can see, sure enough, if I take that vector and subtract it from that, again, it doesn't have a location, so you can move it. Take that minus that, it's the exact same vector. Okay? So the takeaway from this, and it just falls out of the math, is that if you have 2 points on a body, and that body moves, who cares what path it is, it's just some delta t later, you take a snapshot, and you take the difference of those, you take the difference of the displacement of both of those points, then you get the displacement difference vector. Or you could take the position difference of those points at delta t later and subtract it from the position difference of those points at t equals 0, and you get the same vector. And that vector would be the translation of one of those points caused only by the rotation about the other point. Okay? It's very complicated. Anyway, rewind and hear me say those things a million times, because and I said those things multiple times, and then just follow what I'm saying here. And you'll eventually get get this concept wrapped around your mind, as well as the conventions. When we use primes, when we just use one letter, when we use 2 letters, when we use deltas, these things are important. And make sure you get the difference between position difference, displacement, and displacement difference vectors. Those are 3 different kinds of vectors that are important for you to understand and know the differences between them. Okay, and I guess no pun intended there. Okay, so now let's say this of course works in 3 dimensions. Okay, so say you have this 3-dimensional bar that here's your global coordinate system x, y, z. Notice it follows the right-hand rule, and you've got this bar here, and at this corner there's a point P, and at that corner there's a point Q. Okay, and this bar is where it is at time t equals 0. And it moves around who knows what path, but at some delta t later, it's now translated essentially and rotated. It's essentially here. So we go from that point to that point. So just ignore this bar for a second. Just say time t equals 0, it's there, and at time t equals delta t, some delta t later, it's there. Okay, and it went on some weird path. Who cares about the path? It's just we know the 2 different snapshots in time. Okay, of course, here's P prime, and here's Q prime. Okay, and here's P and there's Q where it started. Okay, so let's look at the displacement vectors of those guys, of P and Q. So of course the displacement vector of P is RP prime minus RP, which would be delta RP. So that's how much P is displaced. And then to find the displacement of Q, you take RQ prime minus RQ, which is delta RQ. That's how much Q has displaced. And if you now take the difference of those displacements, so you take this delta RP and subtract delta RQ, and it's this minus this, which you could just think of this guy moving down there. See, this is delta RQ, it's dotted. So take this minus that, and it's this. Okay, and so that should tell you the displacement of P caused solely by the rotational component of Q, or caused solely by the rotation of an axis about Q to get from this position to that position. And you can see if we like kind of take this and translate it purely so we align Q with Q prime, then now it's like that. And you think about in 3 dimensions, in 2 dimensions, it's very easy. The axis of rotation is always coming out of the plane. But for this, the axis of rotation is this dotted black line that always goes through Q, because you took P and subtracted from Q first, so you're looking at Q, okay, and then you're seeing, here's how P rotates around this. Okay, so this is the path P would actually take, and it started there, and it goes up along this arc there, okay? But again, the path doesn't matter, it's the displacement of, it's the displacement of P caused by the rotation about Q. Okay, so if you can see, it's kind of like a cone, if you will, where the tip of the cone is right at Q, and then it opens up like the ice cream cone into this big circle, and in the center of that circle, the center of the cone, is the axis that it's rotating through, going through Q. Okay, so I'm just going to go back here and show you this again, just to, okay, so remember, this was the displacement of this. If we start with this one and minus it from this one, then what we're going to get is as if this moved up there, rotated about Q. Here the axis is out of the page, and we're getting the displacement of P caused solely by the rotation about Q. In 3-dimensional land, let's go back here, we get this displacement. We started with P minus this displacement Q. Okay, and now we're going to get the displacement of P caused by solely the rotation about Q of this axis. And here we translate this over to overlap Q with Q prime, and we rotate around. Remember, if we had taken this and subtracted from this, it would be a different picture, right? We would now align this with that, with Q, and it would now, the axis would rotate through P, and we'd have a displacement going that way, okay? And we'd find how much Q is displaced caused by rotation about P. It just depends on which order you do and what you're interested in finding, okay? So that's the displacement difference vector. And remember, we found it by taking the displacement, subtracting it from this, and we got it. But remember, we could also take the position difference and subtract those at different times. So check it out. If we do RPQ prime, that's the position difference between Q and P at the prime configuration. And if we take that vector and subtract it from the original position difference vector, which is RP minus RQ, which is RPQ right here. So if we take that vector and subtract it from that vector, we can move this over here, take that minus that, and we get the same vector. So again, I've proven both in 2-dimension and in 3-dimension that if you take the displacement difference, or if you take the position vectors at different times and take the difference between those, they all result in the displacement difference vector, okay, which is the delta RPQ. Okay, so pretty darn confusing, but let's look at Eulers Theorem. So it's important to point out Eulers Theorem states that this is essentially what we've proven, right? It states that any displacement of a rigid body is equivalent to the sum of a net translation of one point and a net rotation of the body about that point. So in other words, look, you can break, no matter what I do to this object, if I start here at time t equals 0, and then I don't care what it does, and I stop here at time t equals delta t, to get from there to the original, there was always some pure translation of a point, and then some rotation about that point to get to that configuration. And the translational component is the delta, this guy, and then the rotation is about this to get to there. Okay? So that's the point. And again, it's not about a path. We don't care about the path it takes. And it's all kind of relative to which points you subtract from what. But you can break any two positions down into a translation and a rotation about the point that you translated. Okay? And understanding those vectors and the differences is going to be really key. Okay? So one thing we can learn from Eulers' theorem, okay, which is essentially what we've been talking about here, is that if the displacement difference vector between two bodies is 0, it's essentially a pure rotation. So for instance, say you have a body that starts here, there's a P, there's a Q, you can pick any P and Q you want, and then you track it some delta t later. It slid along this slot and it rotated right there. So the displacement of q is delta rq, it's this, and the displacement of p is going to be delta rp. And if we take the difference between these, it'll obviously not be 0. Okay, it will, if you take this minus this, then you'll slide up there and we'll find how much, q, translated as a result of rotating around p, right? But anyway, the point is that if delta rpq, the displacement difference vector of these things, is not 0, then it obviously rotated, okay? If the displacement difference vector is 0 and these points translated, so p and q translated, then these vectors are going to be the same. And that means if I take any p or q along this and they all translate the same, or they all displace the same amount, so they have the same displacement vectors, and you subtract them, they equal 0, that by definition means there was no rotation. That means you didn't displace anything about any point as a result of rotation. And so there wasn't a rotation. Okay, there's one caveat to this rule. So there's one exception. Don't always think if the delta rpq vector is 0, it's a rotation. It usually is, but the only exception, okay, is for instance, say you had an extruded beam out of the page here, where this corner was p, and if we go into the page as far as the extrusion, there's the other corner, it's q, is directly behind p, okay? And that's the first snapshot in time. Then at delta t later, it actually rotates around that axis defined by p and q till it's in this configuration. So at that delta t time later, p prime is there, and q prime is directly behind it. Well, if you do that, then technically there obviously was a rotation going, and this rotated from there to there, but neither p or q displaced. So their displacements are 0, and so their displacement difference is 0, and therefore the displacement difference vector is 0. And of course, p did not translate according to any rotation about q or displace, and so it's kind of an exception, right? Because we said if this equals 0, that's because there's no rotation. But here there's obviously a rotation, okay? And the difference is because neither of them displaced. So the full rule is if either p or q or both displace and their displacement difference vector is 0, then it's a pure translation. Okay. Otherwise it could be a rotation, right? Okay, so now let's look at the last two kind of things. Apparent displacement is actually pretty easy still. Remember I taught you about apparent stuff and the convention of that earlier about relative, or these conventions of slash with respect to stuff. This will add one more level of complexity, but it's really not that bad. Okay, so say you have this global coordinate system where origin is 0, and it's labeled 1. Okay, then you have another coordinate system which is attached to like a link 2. Okay, this is say link 2 here. You can see it's got its own x2, y2, z2, and then you've got another coordinate system here that is the same coordinate system, for link 2, but at a delta t later. Okay, so you can see these are primed. Okay, so it started out here, and then it moved there at some delta t later. Okay, but the trick is there's another link on there that moves relative to link 2. This is where the apparent stuff comes in. So you've got a slot cut in link 2, and there's a pin that slides link 3 in link 2, and we're kind of curious, what is finding the absolute positions of link 3. Using the relative positions with respect to 2. Okay, but it's really easy. If all these vectors are defined with respect to the global coordinate system, then you can take, say in this, there's one other important point. At this initial snapshot when t equals 0, there's a p on 2 that's p2 that is coincident with the p on 3 that's p3. Okay, and then some delta t later, p2 stays there, but p3 has now moved on. Okay, so that's kind of a key thing. So here at the beginning here, what you do is you take the displacement of rp2, and this is the absolute displacement of p2. That's p2 started here on the slider, and now it went here. and its displacement is basically rp2 prime minus rp2, and that's delta rp2. That's the displacement of p2, okay? And that's the absolute displacement, okay? Well, if we add that absolute displacement to the relative displacement of p3 with respect to 2, and that's where this apparent stuff comes in. Remember, if you take rp3 prime, right, the displacement of p3 from there to there, that's the displacement of p3 relative or with respect to 2, that's the slash convention, /2 relative with respect to 2, then that's the displacement from there. So if you add this plus this, where they're both defined with respect to the global coordinate system, then you'll get the absolute displacement, this plus this obviously equals this, the absolute displacement delta rp3 of p3 on length 3. Okay? So you got to start kind of getting the difference in absolute displacements and relative displacements of a body sliding on another body and how they simply add together to get the absolute. Okay, so stare at it, read this a little bit, and it should make some sense. Okay. Okay, now I'll just conclude with some even more confusing thoughts for you to kind of start wrapping your mind around. To understand angular displacements a little bit. So consider this body, here's a global coordinate system, and watch this body move, okay? So watch this. So we're going to start it going here. All right, so there it goes. It does this weird, this crazy spiral. Okay, so the question is, how much did the body rotate? Well, the answer is never. It never rotated at any time. It just experienced translational displacements along a spiral path, okay? So, just so you understand the difference between translation and rotation, that was all translational motion in some kooky path, but it never changed its orientation. You only rotate when you change your orientation. So for instance, if it did this, then, it clearly rotated around this axis, and the question is, how much did it rotate? Well, let's say 45 degrees it rotated, okay? Now, does that mean everything just rotated? Well, yes, everything rotated, but these points, like that corner's translated. This corner translated. In fact, every point on this body translated from here to here. You can see these points are translating. The only point that didn't translate was this. So the axis that it rotated around, that's the point where it had 0 translation. All the other points translated. But the body and every part on the body did rotate. If you stuck a coordinate system on all the parts on the body, they all would have rotated 45 degrees. Okay? So now look at this one. Let's consider this motion path from there to there. That's, the initial one was t is 0, and here is t, delta t later. Okay? And we don't care about the path. We just care about the initial and final. Because you can know everything you need to from that. Okay, so you can say, well, did the body rotate? It absolutely did. How much? Same amount, 45 degrees. Okay, and of course there was a lot of translations of all the other points. Okay, and it probably had some moving axis of rotation along its path where the speed, the displacement speed was 0. Okay. Okay, so the purpose of these slides was, not only to confuse you, was to help distinguish between rotation and translation motions in your mind. They're pretty mysterious and interesting to think about. So just to confuse you even more, imagine a rotation of this block coming out of the page at you. Okay, as we move that rotational axis further away, you can see the block actually starts rotating less and less, and it actually starts translating more and more, okay? Because the axis, because the radius of the rotation gets larger and larger. So it's actually a mathematical fact that once that axis of rotation reaches infinitely far away, then this is moving with a pure translation. Okay, so that is to say that a pure translation is truly a rotation which is, first of all, oriented perpendicular to it, but displaced infinitely far away. Okay, so that's an interesting thought, and we're going to use that later. Okay. Okay, the other kind of confusing thing about rotation is that you can't add the vectors. So, you can imagine if you had some body and you translated it up and then translated over. That's two vectors. There's a vector up and a vector over. The final position is just here, right? Well, the order that you add those vectors doesn't matter with translations. You could move it over and then move it up. And as long as the same vector moving it over and the same vector moving it up, whichever order you chose to go in the path, it'll end up in the exact same spot. Well, that's not true of rotations, right? So imagine this body began here, and you're first going to rotate around the y-axis, and then you're going to rotate around the x-axis. Well, you'll first get this, then you get this. So we started there and we end there. Well, now, what if we first rotate around the x-axis, starting in the same position, we flip there, and then we rotate around the y-axis, we go there. So just by, we rotated both about the two exact same axis, we just did it in a different order, and we started in the same position, but we ended there and we ended there, totally different positions. So rotations don't behave similar to translations in that regard, okay? So anyway, it's something you should definitely know. But with that in mind, I've very likely confused you a lot. Go back and view this video a lot. Stare at the slides. Look at them carefully and practice some problems. And hopefully by the end of this, you're a master of translations, rotations, and position analysis, these things, okay? So we'll pick up in the next video with the next and third topic, velocity analysis, okay? So thanks for listening.